Hi, everyone. Welcome to week 5 of our 6-week Introduction to Machine Learning series, where we're going to be focusing on the intersection between classification and regression this week. It's really great to see participants from all over the world tuning in for this session. Thank you, everyone, for joining. Before we start, I want to do a round of recognition for the leaders who've been instrumental in putting the content for the series together. First, I want to recognize them for having worked tirelessly to get together this free content for our community. Thank you so much to our leaders. All of them are present as panelists too in this session and will be helping to answer live Q&A and give any support you need. Please feel free to reach out to them on the chat through Zoom if you face any issues or if you need anything at all, and also on Slack during the series if you need any support at all. Big thanks to our sponsor, Home Depot, for sponsoring much needed events at a needed time. And some housekeeping before we begin. If I mention any links during the series, during the session, any links that I mentioned will be shared in the chat. So keep an eye on the chat if you see any links being mentioned. If you have any questions during the session, use the Q&A box to post your questions. If you see any questions in there you would like to know the answer for, please upvote those questions too. Third and final thing, if you have any issues, like I mentioned, you can use the chat to post about your issues or feel free to chat with the panelists directly. We are here to help you out and to answer any questions you have. So feel free to reach out to us with any issues or any questions you have. So finally, welcome to this session. We will focus on two families of classification based on continuous data. These two families of algorithms that we are going to be focusing on are logistic regression and support vector machines. So let's begin. So as always, our 2-hour session is broken down to 2 parts. The first hour, we would be focusing on the concepts and problems in hand. In this session, I would be going over this. I'm Subhana Ravikrishnan. The second half, we will be going over the concepts we learned, implementing them on a real life data sets. This will be covered by Chinmay Hota in the second part of the session. So let's step back and analyze our timeline till now. We've come a long way since we started. We started at the basics of understanding what a machine learning algorithm means mathematically and understanding the different types of machine learning algorithms. We picked supervised as the main one to focus on for these 6 weeks. Till now, we've covered a few classification and regression algorithms which are based on probability, statistics, and linear algebra. This session, we're going to be focusing on non-linearly separable data and families of algorithms that are present to solve this. So let's jump to it. So first up, I'm just going to revisit an example from last week for linear regression, where we saw the heights and weights of a given population being plotted along the X and Y axis respectively. And this forms a plot as shown on the left over here. With this plot, our goal with linear regression is to find a line that best fits all of these points and produces the least loss or cost. So this is the goal of linear regression, which is to fit a line to your given data points where this line best fits your data. If you missed this session, please feel free to check out the video linked in the slide from our previous session to see and understand the reasoning behind this. So now let's see what we want to do with this data. So on the right here is something that we've done till now. Given a set of data points, find a line that fits this data best and produces the least loss. What if we convert this regression problem where we plot a line in your given data set into a classification problem where I instead plot a line which defines a boundary between two different classes. So I know any new data point that comes in would would be present on either side of this line. So instead of finding the formula of a line that fits our data, what if we flip it around? Instead of trying to find the data or fitting our data into a line or plane as is with regression, what if we find a line which separates our data to fit it the best? So this is the intuitive thought behind using regression algorithms for classification. So summarizing what we went over in the previous slide, um, we want to formulate a classification problem based on a regression model. So we can do this by making our regression model predict a continuous value between 0 to 1 and interpreting this value as a probability of it belonging to a class. So we can convert continuous values into categorical by decoding them as true or false with a given threshold. We will go over this in the future slides. So the target would basically be to predict a binary target variable with a logistic function. So let's take a step back to understand what a logistic function means. So a logistic function is a curve which follows the formula shown here, where y is equal to 1 divided by 1 plus e power minus x, where for any value of x, a y value is produced. And if we plot these lines in a graph, it would produce a curve as shown here. This is known as an S-shaped curve as it forms a S shape as seen here. And it's also known as the sigmoid curve. So this curve basically exists in a range on the y-axis from 0 to 1 and for any values along your x-axis. So coming back to our comparison of linear versus logistic, we saw the blue line here last session where we generated a linear model for our data points. And this linear model is defined by y is equal to b naught plus b1x, where b naught is an arbitrary constant value and b1 is associated with each input feature. B naught and B1 are optimized using gradient descent and loss functions to optimize the cost or loss of the y function that we produce. So this is linear regression, and this is the blue line that we see in the graph here. So the orange line is what we hope to achieve. This is a logistic model, and instead we formulate it as shown here, where the model doesn't produce y as the result, it rather produces p as the result, which is probability of it belonging to a given class. And the formula is put together using a similar way. Instead of x, we replace it as b1x plus b naught, as it needs to have a constant value it can have a variation over. So some examples where logistic regression can be used is predicting whether email is safe or suspicious, that is spam or ham. Classifying a tumor to be malignant or benign, categorizing a loan application to be risky or safe, assessing sentiment of a corpus of comments to be positive or negative. So as you see here, the classes that are being predicted are binary in nature. It can have only 2 class values, and we are predicting based on a set of input features. So let's elaborate a little bit on this, and based on the input and output features, define the different types of logistic regression that are there. So in total, there are 3 types of logistic regression. We have the binary logistic regression, which is the one we saw till now, where the response is categorical in nature and has only 2 possible outcomes, which is spam or not, cancer or not, and so on. Next up, we have multinomial logistic regression, which has more than 2 classes, which are three or more categories. And since they are categories, they do not have inherent ordering between them. An example for this is predicting what food is preferred by a given person, whether it would be a plant-based meal or a meat-based meal or a mix of both. So this has more than two classes. So this would become a multinomial logistic regression problem. And we also have the option of an ordinal logistic regression where there is ordering between these between these three or more categories. So in this case, it would be an example of, say, predicting the movie rating of a movie given some input features, where a movie rating has can be referenced by another predicted value. So these are the types of logistic regressions. So moving on, let's take a look at a case study. So say you are a newly appointed data scientist with Women Who Code Bank. Your employer, that is Women Who Code, wants you to assess which of their loan applicants they should disperse a loan to. Who should they approve for a loan, pretty much. So your goal is to propose a solution to draw insights from their database of past approvals of loans. So looking at the problem, you would probably have a data set as shown on the right. But let's revisit the left first, the text block right here. So using this data source and other sources available, so you should not be constrained to the data source provided by the employer. You can attach this with publicly available data sources too. A data scientist develops a logistic regression solution to identify which customers to approve loans for. So taking a look at the type of data that we have on the right, a row of data in this table denotes information corresponding to a single loan application. So we have 5 columns here, such as name, account balance, their age, and marital status. And we also have whether the loan was approved or not. So so each row maps to a loan application. And we have different types of variables which are being defined as independent and dependent variables. So let's take a look at what independent and dependent variables mean. So dependent variables are variables which are the ones which are being tested and measured in a scientific experience, which also means it is the one that is being predicted by our model. So this dependent variable will change in response to the independent variables. Independent variables are variables in your data set to which, if change is applied, your dependent variable changes. So independent variables are the values that are changed or controlled in a scientific experiment. So the changes are controlled in this case by the experimenter, who would be the data scientist. So let's step back and take a look at examples of what independent and dependent variables would be. So let's take our first example of spam classification. So your dependent variable here is to predict whether your email is spam or ham. So that would be a 1 or 0 in this case, and that is a dependent variable. Your independent variables would be the corpus of email or text information that's present about the sender, about the email itself, which can be used to predict whether the email is spam or ham. Another example is doing sentiment analysis on reviews. So here your dependent variable would be the consumer's sentiment about a restaurant. In this case, it can be a positive sentiment or a negative sentiment, which you can force it to be within a binary class, or you can expand it more to be neutral, positive, and negative too. And the independent variables here would be the restaurant reviews text. And this is converted to a data format which can be used by the logistic regression function. Okay, so some more terms before we jump into logistic regression and the math behind it. The first concept that we are going to use is called odds. and which is a new probability concept which is used in logistic regression. So we know that probability is the ratio of something happening to everything that could happen. Odds are basically the ratio of something happening to something that's not happening. So in this case, odds are only for binary classes. So if I have three classes A, B, and C, probability of A would be probability of A happening against it not happening entirely. The odds would be the probability of A versus it not happening entirely, and does not depend on what class the target variable sits in. So odds would basically be P of success by P of failure. And note that this can be any two class problem. If it's a true or false, it can be a P of true by P of false and anything of that sort. And since it's a binary class, one is success. If success is equal to X, failure is equal to 1 minus X, because that's how probability is set up. So we can simplify the formula for odds to be P by 1 minus P, where P is the probability of success of it belonging to a given class. We will elaborate further on these concepts to see how these are used in logistic regression. But let's get introduced to these concepts first. Next up, we have log transformation. Log transformation is another concept that is used in logistic regression, with coupled together with our odds. So log transformation is basically a method to make highly skewed data distributions less skewed. So let's take a look at the graphs on the right over here. So on the top graph, we have a given data set that is provided to you, which is the population of per million people versus area in 100 square kilometers, 10K square kilometers. So plotting these points, all the points seem to be crowded up towards this, and we're not able to actually see any dependencies or any patterns that can be recognizable in this area. So our job is to be able to expand this area and view it in a different dimension so that we can analyze and find patterns in this data. So in this case, say I apply a log base 10 on both X and Y axis and plot these points. This data can be converted to a data in a higher dimension, which provides a little more clarity on how the data points look and are related to each other. So this is definitely very valuable for making patterns in data more interpretable, and also helping to meet the assumptions of inferential statistics. So using a combination of odds and log transformation, we are going to be defining something called log odds, which would be used internally as the loss function for logistic regression. So applying a log transformation on odds of an event helps model for the probabilities of an event. So this basically forces the odds to a sigmoid function ranging from 0 to 1. And we can use the output of this to be considered as the probability of the event. Log is defined by probability of success divided by probability of failure, which is P divided by 1 minus P. Our goal is to find the log transformation of this so that it fits in our curve, and to be able to minimize the log transformation of this odds function. So let's step back and see how we transition from linear regression to logistic regression. So you may ask, why can't we use the same loss function that we learned in linear regression for our logistic regression and just change the formula that we're using for f of x, right? So in this case, since we started off in the first block here, which was linear regression, y is equal to b naught plus b1x. And this doesn't fit our data at all. It just produces a line which tries to fit the two classes, but that's not what we're going for. So instead, we reformat this data as we saw with the population data 2 slides ago, so that it can be plotted on a higher dimension and make a split based on that. So we're applying this, applying a sigmoid function on it, which is basically converting all of our x values to probabilities based on this formula right here. And once we do that, logistic regression will basically optimize on this log of odds that is created. And this would be the loss function that is being used for logistic regression, where it optimizes the log odds instead of optimizing just the loss function. So, so as far as the loss function goes, it's not very simple to formulate the loss or cost for logistic regression. Let's take a look at what the reason behind this might be. So we saw before that the loss function for linear regression produces a convex curve. So once we start at one end or the other end of the curve, it would be as easy as a ball rolling down to the global minimum to find the global minimum of this curve. What if you have a non-convex curve where the ball starts rolling from one end and reaches something that it thinks is the global minimum, but actually isn't the global minimum? And there is no way for it to get out of the saddle point to get back to the global minimum. So revisiting this, since our data is not linear in nature, it is the loss function doesn't turn out to be convex in nature. So this makes it a kind of hard optimization problem. And it's not a very straightforward way to find the global minimum due to these saddle points, which make a point think it is at a global minimum, even though there's a global minimum further than the local maximum. So there is no concept of residual also, since what we're predicting is going to be a class, and the class can be either right or wrong, and not how right or how wrong the value is, as we need for regression. So let's see how we can define this cost. So on the top right here, we have the function that we're defining as the cost for two possible values of what y could be. Here, y is the actual value of the target response. Y cap is our predicted value from our model. And our goal is to find the difference or distance between these two and define that as the cost of your model. So in this case, we are going to define two possible options for when y is equal to 0 and y is equal to 1. And we're going to look at them separately. So let's take a look for the case where y is equal to 1. And we're going to apply the formula log of y bar. So in the case where y is equal to 1, which is the graph here on the left, when y bar is equal to 1, in this case, log 1, as we know, would be 0. So which would make the cost tend to 0. So when for y is equal to 1, only the first statement that we're looking at here, when y bar is equal to 1, cost is equal to 0, right here, where we have y bar on the x-axis in the graph here, which is also known as the hypothesis of x, h of x. And on the y-axis, we have the cost of predicting that y bar value. So when y bar is equal to 1 for y is equal to 1, the cost is 0. And as we deviate away from the right prediction, that is, as y bar tends to be 0, the cost becomes way higher. This seems like an intuitive way to perform for this subset of data, because when y is equal to 1, I want the cost to be as minimal as possible because I'm making the right prediction. And when y is equal to 0, I want the cost to be as maximum as possible so that I penalize this decision as much as possible. So on the flip side, it's the same thing for the case where y is equal to 0, where the predicted class is equal to 0. Then when y cap is equal to 0, cost is equal to 0, because it's again log of 1 when you replace y cap in this formula right here. So you start for when y cap is equal to 0, cost is equal to 0. That seems right, because here in this case, y cap is equal to y, which means our prediction is correct and cost should be minimum. As y tends to 1, the cost tends to infinity. As my prediction deviates away from the actual value, my cost tends to infinity. So this formulation seems like an intuitive way for us to formulate the cost of a given data point or a given prediction. So we need to aggregate both these together to a single formula so that that formula can be applied on all points regardless of whether y is equal to 1 or y is equal to 0. Because a loss function, we can't have multiple options or branches which it can traverse. We want it to have one single solution it can apply. So in this case, we aggregate our solution into this formula right here, which is basically just a summation of this value into this value and this value into this value. So it's yi into log yi and 1 minus yi into log of 1 minus y cap I. So you have your prediction inside your log and the actuals outside your log. Let's see how this actually makes sense. So if y cap is equal to 1, that is your prediction is equal to 1 minus y cap is equal to 0. So if your prediction is equal to 1 minus y cap would become 0, and this log 0 is undefined. So we have only this term left to calculate in the case where we're predicting y cap is equal to 0, which corresponds to this value. And on the flip side, it's the same. When y cap is equal to 0, we would be left behind with only this term to calculate. This value also tends to be as minimal as possible, having no effect. And this value also will be as minimal as possible, having no effect. So we're able to consolidate this into a single formula by adding a factor, a multiplicative factor in the beginning, which nullifies a given log value, or a log value which nullifies the factor that we've added. So this is the log function that we will define for our model. So moving on, now that we know what loss function we want to use, similar to what we saw in linear regression, we need to minimize the cost that we are seeing. So on the right here, we have the cost to intercept curve. For a convex curve, it's going to be pretty and nice like this, where we start rolling the ball from one end and it reaches the global minimum. So since we've converted our non-convex curve into a convex curve using the previous slide, we can now apply stochastic gradient descent using partial derivative until the gradient descent converges at the global minimum. And we can use this value to plug it back into our logistic regression intercept values. So we went over the stochastic gradient descent in detail last week. If you have any questions, you can check out this video to see our explanation for it. So next up, there's another terminology I want to introduce, which is the decision boundary. A decision boundary is basically a line that separates training examples into two or more distinct spaces. So in the graph that we see here, graph A shows a given line splitting your data into two given classes. So this is what we expect logistic regression to do, where I have two sets of classes and I can define a decision boundary which splits up my classes in the best possible way. So this is linearly separable data. On the right here in graph B, we have non-linearly separable data, where some of your data points may be crowded up in the middle, and the line that we have to generate to split our classes might not be linear in nature, as you see here. This line is linear in nature, while this line is not linear in nature. So this is what a decision boundary is. An example of a decision boundary is this graph that you see here, revisiting our example of height to weight plot. So this height to weight plot also has whether the person or the data point was male or female. So in this case, from the example, I can define a decision boundary or a decision plane to exist over here so that it splits up my data into the best possible two parts. So our logistic function's goal is to find the best possible line that can do the split. So in logistic regression, as we saw, the logistic regression is considered linear because the decision boundary can be a line if you consider 2D data, and a hyperplane if you consider 3D or higher dimension data. So we need to find a threshold, which is basically the decision boundary that you see here, to be able to define what is the cutoff where you decide which side, which class a given point belongs to. So even though I do devise this line, what if my data point lies closer to the center or closer in this line? How do I decide what class it belongs to? For this, we use thresholding, where you decide a given threshold, in this case, 0.5 as the threshold. Everything that's below 0.5 would belong to one class, and everything that's above 0.5 would belong to another class. So this decision boundary is an iterative process, and you basically iterate through multiple possible combinations to see what is the best decision boundary with the minimum cost. And this is defined by epochs, as you see up here, where epoch is basically a given iteration to find our best possible solution. So we are all done with logistic regression, and we're going to move into our next class of families, which is support vector machines. So support vector machines are a class of algorithms that can be used for classification and regression. Based on the intuition, it's based on the intuition of finding a decision boundary that separates your data. So we remember that logistic regression did the exact same, where it found a decision boundary that separates your data. But then this decision boundary can only be found on linearly separable data we saw for logistic regression. So maybe support vector machines is giving added value to this. Let's see what it actually does. So let's revisit our example from before, where we had the women who code bank case study, where your employer would reach out to you with a given data set of loan applications and whether the loan was approved or not. So your goal would be to consolidate this data into, say, this format. I've stitched this together with additional data set. Before we didn't have the yearly income. Now I've added in a yearly income column too. And I finalized that these are the independent variables that I want to be focusing on to produce the output of this dependent variable. So in this case, each row can now be converted to a data point in a 3D representation. So this 3D representation is only because I have 3 independent variables. If you have n independent variables, this would become an n dimension problem. So in this case, I'm going to be plotting account balance along the x-axis, age along the y-axis, and yearly income along the z-axis. And so each of these can be converted to a data point, x, y, and z. And each of these data points can be plotted in your given graph and then color coded with red or green based on whether the loan was approved or not. And our goal could be visually to find a hyperplane that splits our data. So now that we saw that, let's take a look at the logical intuition behind support vector machines. So support vector machines basically try to find a dividing hyperplane or a decision boundary between two classes so that it provides the biggest margin between the two classes. So let's revisit the non-linearly separable data that we saw before. This is something that logistic regression cannot handle, as we saw, since the line that logistic regression produces is a straight line, and this would require us to find a decision boundary that's circular in nature. So what do you do when you have a non-linearly separable data is the main question. So the mathematical intuition behind support vector machines is that a non-linearly separable data set can be converted to a linearly separable data set in a higher dimension space. So a 2D data set from this is converted to a 3D data set where a z-axis is added in. And this z-axis basically provides height to our data points. And now I can introduce a nice hyperplane right here that divides my data set accordingly. So this is an option that we can use. And that is the mathematical intuition behind support vector machines, is when you have a a given data set with say n dimensions, convert that to m dimensions, which is greater than n, and find a decision hyperplane in this plot. So let's revisit some terminology that we would be using more often. So the first one is the decision hyperplane. This is similar to decision boundary, but it's called the hyperplane since we're increasing the number of dimensions that we're working on. This would be a higher dimension and it's called a hyperplane instead. So the hyperplane is the plane that divides your two classes. Next up, we have support vectors. Support vectors are basically the points closest to the decision hyperplane, which is on either side of the decision hyperplane. So in this case, these 3 points are the closest on the class 1 side. These 2 points are the closest on the class 2 side. And these are called the support vectors of our support vector machine. Margin is basically the distance between the support vectors of each classes. The biggest, so the distance between the two classes right here is called the margin. And the goal of SVM would be to find the margin maximizing decision hyperplane. So we need to have this distance as maximum as possible to produce a data set which is as separable as possible to produce the best results. So let's take a look at some of the math behind the decision hyperplane. So before we take a look at the math, I want to point you to this video right here, which is marked up top. So this is a great resource for understanding the math behind SVM, and the screenshots right here have been grabbed from that video. I encourage you all to check it out and get a better understanding on the intuition behind the mathematical part of logistic regression. So in this case, our point is X, as we saw with our Women Who Code bank case study, where we have 3 dimensions: account balance, age, and yearly income. So X would basically be X comma Y comma Z, a given data point in that space. Second up, what is a decision boundary? A decision boundary is a line which can be defined that splits our data set based on this formula that you see here, W transpose of a function of X plus B, which is the bias, is equal to 0. We will revisit this formula shortly. And once you find out the formula of a decision plane, our goal would be basically to then find the distance of our support vectors, which is basically the closest point on either side. And you can find the distance of that support vector to your decision plane using geometric algebra formulas. So once you have that together, say the case where you have perfect separation, where your data set looks like it can be separable right off the bat, but I can have multiple different lines which I could possibly plot, and I need to find out which one is the best one to use. And for this, we use our loss function to see which line produces the least loss or the least cost, and use that as the final decision hyperplane. So that can be done as follows, where we find out the weight using an argmax and produce the hypothesis line or the support vector machine line, the decision boundary, as the one which has the minimal cost incurred. So checking out the formula that we have, just want to get rid of this bottom panel. Okay, I hope it disappears off. Okay, I think it should disappear in a second. Okay, perfect. So moving back one slide, the formula we have defined as follows. So y cap is the value we want to predict. So we predict the value y cap based on a combination of our input features x1, x2 till xn. Each x1, x2 till xn is weighted by a weight vector, and these are defined as w1, w2. And then we have a intercept value, which is w0, that we add to our formula. So this formula can be simplified to this as shown, where all the values past W naught can be compressed together with a summation. And for all M values in my, for M features that I input, or the M dependent variables that I input, I predict this, M independent variables, I predict this dependent variable. So since we saw that X is only numerical in nature in this, and basically represents a given data point in a vector space, we can consider this as a matrix multiplication of sorts, because each X value is a data point of coordinates. So therefore, we can summarize this formula as y cap is equal to W naught, which will be intercept value plus the weight matrix into our input feature X matrix. So revisiting the linear regression that we saw last week, we saw linear regression is defined as y is equal to b1 x1 plus b naught. And if there are more x values, this would be the summation at that level. And the b1 we're using here is a slope. The b naught is the y-intercept. And if you see the formula for support vector machines, it looks pretty similar, where we're producing our target response y cap is equal to W naught, which is comparable to B naught right here, into a weight plus a weight into X, plus a weight into X. So the formula and the intuition is the same, but then the dimensions in which it is deployed differ. That is the biggest difference between the two. So in this case, we have, we're defining W naught to be called the bias term. That's a terminology to remember. W transpose is your weight vector. So if I have three input features in X, which are the account balance, the age, and my yearly income, as 3 points, say 5,000, 45, and 10,000, my weight transpose matrix would be basically the weights corresponding to these three values, which would be W1, W2, and W3. And I'm transposing it because you need it to be transposed for it to do a matrix multiplication between two vectors. So that is the intuition behind this. So, visiting the diagram that we're seeing on the right, support vector machines, the goal is to basically find a decision hyperplane, as denoted by the black line right here, which best separates two classes denoted by X's and O's right here, to be able to produce this line. Once we have this line, we produce two more lines on either side based on the closest support vectors of the classes on either side. And once this line is produced, we can classify any new data point in our data set. Consider 7 and 8 weren't present in our training data set. The other data points were used to produce this line. And now I want to make a prediction for 7 and 8. So there are two possible ways we can go about making this prediction based on the two types of margins that can be defined. One is a hard margin and the soft margin. And let's take a look at how the predictions for 7 and 8 would change based on what kind of margins are used for SVM. So first up, we have the hard margin. So hard margin is when the model will not make prediction for points falling within the margin. Any points falling within this margin will not get a prediction for those points. So this basically goes under the assumption that data is linearly separable, that I will not see an overlap of data points in this space. So forcing rigid margins can result in a model that performs perfectly in your training data, but could possibly be overfit or less generalizable in your testing data. And in this case, identifying the best cost is probably related to the specific data you're working with. In this case, that means based on your data, misclassifying this data point can have a higher or lower cost based on how bad the impact is going to be. So let's take the case that this is a spam and ham problem. So misclassifying whether it's spam or not might have lesser cost in comparison to a problem where you're detecting whether it's cancer or not. So the impact of the problem in hand has a say in which in the cost function you're defining for your function too. So that is hard margin. So let's take a look at what soft margin means. So soft margin is basically going under the assumption that your data is not linearly separable. There will be overlap. I will see data points in this margin right here. I don't want my model to not make a prediction. I want my model to make as good a prediction as possible in this margin and go with it. So for this, we bring the soft margin method and we introduce a new variable called slack, which is denoted as so. So every data point in your data set has a corresponding slack variable. So this slack variable is basically the distance of a data point from its class margin. So in this case, we have two misclassified examples right here. One that falls within the margin, one that falls on the wrong side of the margin. So first one, let's take a look at is this point. Let's say this point is I. So xi lies a little distance away from the decision boundary decided for other members of its class. So the corresponding slack variable for this xi would be this slack variable that's introduced, which is the actual Euclidean distance between this point and the decision boundary for this class. Similarly, we see a point J right here, which is way beyond the misclassified line decision boundary for its own class over here. So in this case, the slack variable for this is the distance, how far away it is from its own decision boundary. So intuitively, this basically penalizes data points that are more further away from its own decision boundary than ones that are closer. So this data point predicting it as this class might have lesser penalty involved compared to this data point, which is way farther away and actually in the wrong class. So this ensures that points in the middle or the points in the overlap region can be predicted. And even if they are predicted, they are given way more penalty to make sure that the predictions aren't chaotic in nature. And coming down to the coolest part of SVMs, which is a buzzword, everyone would have heard about it, which is kernels. So kernels are a really cool feature of SVM. It's kind of a buzzword, so let's try to decode it to understand what exactly kernels do. So kernel methods are a class of algorithms used for pattern analysis. Pattern analysis is used to find and study general types of relationships in data sets like clustering, ranking, correlation, and so on. So kernel methods operate in a high dimensional implicit feature space without computing the coordinates of the data in that space, but rather by simply computing the inner products between the images of all pairs of data in the feature space. So let's pause here and revisit this statement. Previously, we saw a two-dimensional data can be converted to a three-dimensional data, right? So my data points coordinates in the two dimensions is going to be different from the data points coordinates in three dimension. It's going to be xi comma yi in two dimensions and xa comma xb comma xc comma xa comma yb comma zc in my higher dimensional vector space. So so this kernel basically, instead of recomputing the coordinates that a data point should have in the higher dimensional data space, instead of calculating that to calculate the distance, does an efficient computation on it. So basically the method makes it computationally cheaper for you to be able to make predictions in higher dimensions without actually calculating the values of where these data points should sit in the higher dimension. So looking at some examples, you will understand this a little better. So the kernel trick is a way of computing the dot product of two vectors x and y because we saw dot products are needed to calculate our y cap for SVM. So it's a way of computing the dot product of two vectors x and y in a feature space. This feature space can be high dimensional. We have been visualizing just 3-dimensional and so on. In real life, this can be up to thousands and millions dimensions too. So this is also known as generalized dot product. So applying a kernel trick in SVM means that you are replacing the dot product of two vectors with a kernel function instead. And kernel function in this case basically produces a generalized dot product. So kernels can be of 3 types. We will look into the math behind the kernels right after this section. So please wait for it. So the first up is a linear kernel. So it works well if your data is linearly separable. And it's not too common to use SVM for linearly separable data sets, since we saw logistic regression does really well with linearly separable data sets. But on the flip side, there may be specific use cases where SVM might prove more useful, depending on the relationship between input features present. So next up, we have a polynomial kernel. So polynomial kernel basically follows the formula that we see here, where we have our two data points, x1 and x2 here. To find the distance between them, we basically introduce a constant term and a degree of the kernel to be able to decode this. So we can calculate the dot product of two vectors by increasing the power of the kernel, which is the degree of the kernel. And this is a pretty popular kernel that is used. So let's try to decode the math behind it. So in the first diagram you see here, this is a really great example of non-linearly separable data. Ignore these data points that you see here and only the data points on the x-axis. This is a good example of dosage data, where the dosage of a given drug is plotted along the x-axis. And the points are marked with red or green based on whether the dose cured their disease or not. So as you can see, those who took the dosage in the right amount, it cured the disease. Those who took lesser than the given right amount or more than the right amount did not cure the disease. So this is a great example for linearly separable data. So say that we raise this to a square value instead of the x value that we see here. So in that case, we convert 1D data that we saw only on our x-axis to 2D data, where we're plotting a y-axis too, which has the corresponding x square value on it. And this is basically plotted to be a line as seen here, which follows the similar pattern of a squared curve. And then now we can just, from visually itself, I can now define a nice neat line here, which separates my data. So this can be used to separate your data into two parts. So how does this map back to the kernel method that we saw? So in this case, say that I'm introducing a constant term 1 by 2. My x1, x2 points are a and b vectors. The degree of the kernel I'm raising it to is 2. So according to general mathematical rules, so if you do a square of this, it basically multiplies it by itself, and that produces this as the output. This can be formulated as a dot product of two vectors instead, which can be as shown here. So a dot product is basically just a product of the first terms added up with the product of the second terms and added up with the product of n terms. So in this case, the first term here is a into b. Second term here is a square into b square. Third term here is 1 by 2 into 1 by 2. Dot product sounds fancy, but basically we are just taking a given equation and converting it into a dot product instead. So now if I do this for, say, a is equal to 1 instead of 1 by 2, I'm keeping the power the same. we get this as the distance value over here, the output of the kernel. The output of the kernel can now be decoded into a dot product. And this can be read as, on the x-axis, everything is offset by a factor of root 2. On the y-axis, everything is at a factor or at a squared factor. And the z-axis has this value. So basically, all we need to do is plug in values into this kernel, which can be the value a, which is a constant term, and the value b, which is the degree of the kernel, to get higher dimensional relationships between these data points. So taking a look at this from an example point of view, say I want to find the distance between these two data points, 9 and 14. I just need to plug it into this formula that we saw 2 slides ago. And this can be decoded as follows into this value that you see right here. So this is basically one of the two-dimensional relationships. This is the distance between the 2D points and not the 1D points. The distance between the 1D points is just 5, if you think about it. But then once you raise it to this line, you want to know the distance of it. So this is a great way for us to find distance of points in higher dimensions without having to calculate the Euclidean distance or actually having to know what coordinates these data points are risen to. And moving on to our last one, this is the Gaussian kernel. So Gaussian kernel is also known as radial basis function, and its value depends on the distance from origin or some reference point. So the differential of d and x, dxij right here, is the Euclidean distance between xi and xj. L that you see here is the length scale of the kernel. The length scale of the kernel basically gives a level of smoothness to your final model. And this is also a really popular kernel that is used. Polynomial and Gaussian are ones that are very popularly used. Linear is not too popular, as logistic might solve the same problem in a simpler way. But linear also, but there might be cases where SVM might prove to be better in a linearly separable problem. So let's take a look at the last few slides in this as we wrap up SVM and I pass it on to the implementation portion. So let's take a look at the advantages. So the advantages is it's really effective in the higher dimension because it doesn't have to recalculate your new coordinates in your n dimension. After calculating the new coordinates, it doesn't have to calculate the Euclidean distance. It's basically found a shortcut way to do this using kernels. So this is very useful when you have number of features that are greater than your training examples. That is, your columns are greater than the number of rows. A good example for this would be gene data, where each row can have thousands of different gene indicators present in it, and the number of columns might be lesser that's needed. So this is useful when you have a small data set which has too many columns. So this is the best algorithm to use when the classes are separable by a decision boundary. And it is definitely best suited for extreme case binary so that we're sure nothing lies within the margin and we don't have to figure out whether we need to do hard or soft margin to deal with this margin error. So the hyperplane is affected only by the support vectors, so outliers don't have impact. So outliers do not impact your decision boundary, but overlap between the classes along the decision boundary will impact your decision boundary. Moving on to the disadvantages. For larger data sets, this might be computationally inefficient because it requires a larger amount of time to process. It does not perform well in the case of overlap classes, as I mentioned before, where the margins are not well defined and there is a lot of overlap within the decision boundary. And then another two biggest disadvantages with SVM is the handles that it gives to the user or the scientist who's experimenting, which is us. It allows us to play around with the hyperparameters that we saw. And it also allows us to play around with the kernel function, and within the kernel function, the hyperparameters associated with that kernel. So this basically gives a lot of different things to play around with, which might turn out to be more of a disadvantage than an advantage. Also, it is very important to pick the appropriate kernel function, and this can be kind of tricky. And maybe it's called kernel trick for a reason. And since we saw support vector machines can take in only discrete data and produce only binary class output, data preparation is essential in this case to make sure that our data is in the right format. And it is possible to convert any data set that you have with you to a data set that can fit support vector machines by discretizing and changing your classes. Any data set can be converted to a format that you can apply SVM on. So let's look at the first point where it is discrete data only. So since the data is plotted in a feature space to find the optimal decision hyperplane, input features need to be discrete in nature. So what do you do if it is categorical in nature? So you can use common discretization methods can be used in this case, such as one-hot encoding and label encoding to convert your continuous values into discrete. And this discrete values can be fed into your model. And SVM also does well for binary classification mainly. So it produces a decision boundary between two classes. So if you have more than two classes, this can be made to fit SVM2 by using two possible methodologies, which is one versus rest and one versus one. Let's take a quick look at some examples for that. So if your target response has three classes, A, B, and C, it will not fit SVM because SVM is a binary model, right? So let's see how to change this up based on one versus rest and one versus one and get a result from SVM. So say we're doing one versus rest, a model is built for each of the following and aggregated. So it basically builds it for each class versus not that class, and they are aggregated in some way across that. So in this case, since we have three classes, this would be A comma not A, B comma not B, and C comma not C. So we will produce three SVM solutions, and these three can be aggregated together using different methodologies to get a solution out of it. So one versus one is basically it builds a model for every single pair of classes that are there in your data. Since we have three classes here, there are three possible pairs of classes that we can produce. So this each would produce a SVM model, and they can be aggregated together in a way. So the aggregation methods for these two would be different because each of the models are built on the entire data. Each of the models are built on different subsets of the data. So the aggregation methodologies should vary based on that. So that's it for this session, the theory part of this session at least. So quickly recapping everything that we have went through till now. We started off with linear regression, saw how it compares against logistic regression, and then we started defining what logistic regression means. We looked at what a sigmoid function is. We saw a bunch of examples and the different types of logistic regression, such as the binary, multinomial, and ordinal. Then we saw two important concepts for the loss function, which was odds and log transformation, which is basically used to create the log odds, which is used as the log loss function that we're using for logistic regression. Now you know where the name logistic comes from. It's because of all the logs that we apply. And we also saw how defining a decision boundary is important and how this can be an iterative process when it comes to logistic regression. Moving on, we saw support vector machines. We saw the intuition behind it, which is it can separate non-linearly separable data, which logistic regression can't. We saw a bunch of terminology associated with it, such as decision hyperplane, support vectors, and margin. We saw its formula with some really good examples. We saw the different types based on the margin, which is the hard margin and soft margin introduces the slack variable. Then we saw the coolest feature of support vector machines, which is its kernels. We saw three different types of kernels, which are the linear, polynomial, and Gaussian. and the pros and cons of each. Then we saw the entire advantages and disadvantages of support vector machines, when you should use it and when you should not. And because of the constraints that come along with support vector machines, how you could possibly prepare your data for it to fit SVM. So this is the entire of the theory that we have planned for this session. And I've just been 6 minutes over time. I'm going to pass it on to Chinmay to pick up for the Google Colab implementation for logistic regression and support vector machine. So I'm passing it on to her now.
Thanks, Sumana. So, welcome everyone. We'll be working through some of the, I hope you guys can see my screen. And if you guys face any issues with the audio or video anytime, just ping us in the chat. And so we will be working through some of the implementation of the concepts we just learned. And for this session, we'll be using SkyKit to implement all the models. We are using SkyKit because it has all of the parameters which Mana just described in the theory session. So there are various parameters which correspond to all of the different concepts we just learned. So we'll be quickly seeing how we can actually use different parameters and then compare our models and how we can actually implement it to predict a real output or predict a real scenario on a real world data set. And so we'll be getting started with a very simple data set, which is one of the standard data sets for any machine learning problem which you get started. This is a iris data set where primarily you just have 4 features, which are the width of sepal width, sepal length, petal width, and petal length. And the task is to predict the category of the flower based on this. This is a very simple data set because this is provided in a way that there is not much pre-processing required. It's already a balanced class and it's already pre-processed to a great extent. And our only task is to fit a machine learning model and predict the outcomes. And so this should be fairly straightforward to work with when we are working on a complicated or complex algorithm like, let's say, SVM, because we do not have to worry about the pre-processing aspects. And we can simply see, or based on intuition, we can just see how the algorithm works. So let's get started. And this is kind of provided. This is one of those data sets which is inbuilt with SkyKit. So you do not have to search for the data set or anything. You can simply load the data set when you import it from SkyKit. So we are basically working through loading our data and then just very basic data exploration. And then we'll be looking into how we can convert categorical values to numeric, because as Sumana explained, a lot of machine learning algorithms or models do not work on categorical data. And then we'll be seeing the relationship between X and Y. And sure. So I'm going to zoom in a little more into the notebook just to make sure that it's clearly visible. We'll be looking into plotting the X relationship between X and Y to see like if it's a linear relationship, or why do we need to apply a model like SVM? Because as long as there is a linear relationship, we should always opt for simpler models. So we'll be looking into the X and Y plotting. Then we'll be just splitting the data. And then for logistic regression, also I just wanted to mention that you might see some differences between the notebook which you have and the notebook which is on my screen. This is because we haven't pushed the latest code to the GitHub yet. So please follow along with me on my screen. And then after the session, we'll be adding the updated notebook to the GitHub for you to refer to later. So like I was mentioning, we'll be walking through the different log linear or linear loss functions, which are different from what we saw in gradient descent in terms of it works on log loss. And so these are the two types of log loss functions we'll be looking into. And then we'll be looking into what effect scaling of data will have on the model. Then we'll be going to support vector machine, where we'll be working on different kinds of kernels, which we just learned about. And then in the end, we'll be evaluating the performance based on some metrics. So these are primarily just a few visualization libraries which we'll be using. And this is this is the part where I was mentioning that scikit-learn already provides a lot of data sets, and iris is one of the data sets. There are a few more which you can import fairly easily and get started on learning any models that you want. Uh, then we'll be using logistic regression SVM, and we'll be visualizing like how the predictions are working with a confusion matrix. And for our metric performance calculation, we are using accuracy score. So this is just a one-step process for getting started with the iris dataset, where you just load it from the datasets. And next step will be exploring the data. So we can see that there are 150 records and 4 columns in the dataset. These 4 columns are purely the dependent variables, and there is one more independent variable or target, which we'll be looking into. Uh, so as we can see, this data set this data which we loaded from Scikit is in NumPy format. So we'll be working on converting it to a data frame first. So this is the standard pandas process of converting a NumPy array to data frame. After that, we'll be storing the target variable in a separate column, column in the same data frame. And so these are the 3 categories of our output labels. So this is a multi-category problem, or a multi-classification problem. Um, and so if we just quickly want to take a quick look at the kind of data we are dealing with, this is just a head function. And if we see, most of the length and width values are floats, which are fairly in a standard range. If we want to, yeah, so fairly in a standard range. Um, so next, we do see that we kind of have these 3 categories which we are dealing with, and so we want to convert those into some kind of uh, labels, or we want to convert those categorical values into numeric values, so that we can actually fit our model and work on it. So to do that, we are currently using label encoding, where we manually assign a tag to one particular value or one particular category, and then we simply map it to that category. So for example, in this, we are assigning 0 to this particular category called Setosa, and so on and so forth. Um, so after this step, where we are mapping each uh, category to its label, we we have our data where everything is numeric, and we can perform or we can fit models on it. Next, we want to see what are the or what is the value count for each category. And so since we see that all of the 3 categories have balanced, so this is a very fairly straightforward and simple data set we are dealing with, where it's completely balanced. Next, we want to see like what is actually the relationship between X and Y, because as Sumana explained, if it's a simpler or a linear relationship, the best model we can choose is something a little more straightforward than SVM. So we kind of want to see if what kind of relationship does X and Y has. And so for this, because I am visualizing it in a 2D plane, I am representing just two features or two variables. And I want to, so for this visualization, I have taken the sepal width and sepal length. You can also do the similar kind of plotting for petal length and petal width. So based on these two, I see that the way there is no linear relationship between sepal width and sepal length for representing these three categories. So there is no one clear linear boundary which I can see based on this visualization. So I would need a slightly more complicated machine learning algorithm to just be able to come up with boundaries or come up with lines for categorizing um, these target values into different categories separately. So next step would be I would be just dividing the data frame into X and Y. And next we'll be splitting, because we have very less data, we'll be making a 80-20 split. So 80% of our data set would be used as training, and just 20% will be used for testing. Um, Next, we just print the head, and we can see that uh, the categories or the labels have been into categories, basically three categories. So next we want to try and fit logistic regression to this data set. So since logistic regression is basically a classification algorithm, we are trying to predict the category of this problem using logistic regression. And we are going to start with the default solver. So when this is solver here, it just basically means one of the optimizing mechanisms. Um, for this, we are trying to optimize the log measures of all of the variables or the log loss. So we are using this particular solver called LPFGS, and the maths behind the solver is quite heavy for us to go to at this stage and be able to understand intuitively. But just to give you an overview, this is really good for when you are working on large data sets, and it just instead of taking a direct derivative of the loss, it takes a second order derivative. So that's basically like saying that you are further scaling the loss uh, further. So it's like the second order derivative of the loss function. So we are going to see how this actually performs for our data set. And we kind of the rest of the parameters which the model uses or Skykit uses by default are as printed. You can play around with this models and see if there is any actual improvement in performance when you're working on it. But for now, I have just used these default values because this gives fairly good performance as for this data set. Um, so next we would be predicting based on the test data. And if we want to see the accuracy, it's 0.93 for this default or this LBFGS solver. So next we go to another solver, which is liblinear. So liblinear is a loss optimization or log loss optimization function, which optimizes the loss with respect to one variable at a time. So it will just take into consideration one of the variable, and it will do its best before moving to another variable. So that's the intuition or the idea behind this function. And it also works well on small data sets. So we are going to try this for our data set, and as we can see, it gives a slightly better performance than the earlier loss function. So it's 0.97. Next, so logistic regression basically tries to have all of our target labels on a scale of 0 to 1. So there is a huge impact of scaling, or let's say that if you scale your data in the pre-processing step before fitting the model, it improves the performance of the model drastically. So to see that, we are going to scale the model and compare how it performed when there was no scaling. So for this, I have picked up the solver where the performance was slightly less. And so for this, I'm currently using standard scaler. So with standard scaler, it would try to scale your, there are different types of scaling mechanisms available, which all can be accessed in this pre-processing library of scikit-learn. And so standard scaler is one of the scaling mechanisms where it would try to scale your data all close to the mean of the mean point of the data set. So this performs well when you're working with a small data set. So let's see how the performance improves if we scale. So this is just describe, which is all of these is actually part of pre-processing, but I just wanted to compare the performance. So I did it at a later stage. And so describe is basically, it will give all the statistics of the data set. So if you see the mean is mean of this column is this, and if we want to see what the variance is, we can refer to um, this column. So we can see that the max variance is with petal length. And so next, when we are trying to, so it is always a good practice to scale to both the input and output features at once. But since our output feature is just categorical and it's not a continuous or a actual regression problem, like let's say a house prediction problem, a house price prediction problem where the prices are on a huge range, or the range of prices is varying from, let's say, 0 to 5,000. So since we are not dealing with such a problem, we are just scaling on the input features and not on the output feature. So this is the line where I have applied the scaling. So basically fit transform, when you apply fit transform, what it does is it fits the data, it fits the scaling on the all of the training data. And at the same step, it also transforms the scaling data, transforms the fitted data to a scaled version. So this is like basically two steps combined, fit and transform. And I have mentioned the column names. And next step, we again went through the splitting and everything, and we are using the default LBFGS. And so yeah, so we try to see the prediction, and the prediction is um, 0.90 for this. But I kind of feel like there is this is primarily due to the max iterations. And if we because we have mentioned the entire 150 as our max iterations, and if we play around with max iterations a little, scaling might actually be able to improve your improve your model performance. So this is all about logistic regression. Next, we move to SVM. And the primary goal of applying SVM on this kind of data set is we are trying to somehow draw a margin in a way that we can draw boundaries between this not linear kind of distinction between the different categories. And so SVM is a very good model for such kind of data types, or such kind of data sets. And so we are going to try a few different kernels of SVM and see how the performance improves and how it actually performs. Um, so we are going to start with the default, the Gaussian kernel, which Sumana explained. This is called RBF in Scikit. And here it just tries to smooth your data. And there are lots of other parameters as well, which you can play with. But for sake of simplicity and just for getting started, I have kept the default parameters. But there are a lot of parameters and there is a lot of maths behind what these mean. And it's like as you move down the line, it's a good idea to play with these parameters and see how it actually affects the performance. So we are going to predict for um, this X test. And when we are starting with the default or the RBF kernel, and for this, if we see it's 0.90, the accuracy score is 0.90. And this confusion matrix is actually the X or the um, rows represent the actually correctly predicted values, and the Y represents the expected or uh, uh, so the X represents the actual values and the Y represents the predicted values, if you have to think about it in a XY coordinate axis. And so all of the values along the diagonals are actually the correct predictions, or these actually help with the accuracy. And if you see the 2 and the 1, these are values which are not correctly predicted. So due to this, there is this 0.9 accuracy. Next, we move to linear SVM, and as we can see in the data set, the relationship is not very linear. And so we kind of intuitively think that linear wouldn't be as well performing. So moving on, um, yeah, so this is where we have defined the kernel, and rest of the parameters we have left it to be the default. And so if we see the performance, it's 0.93. Next step, we move to polynomial kernel, where even if there is not a linear relationship, but there is like a polynomial or exponential kind of relationship between the input and the output. It will try to capture that as well. For example, let's say that the output is directly proportional to the square of the input, or that kind of relationship. It'll still be very good at capturing that. And so for this, when we print is 0.9, the performance. Next, we move to nonlinear SVM. And here, if we see, um, the the nonlinear SVM will actually be performing well on calculating the performance on any kind of or capturing the any kind of non-linear relationship between the input and output. And so this is particularly useful when we have, let's say, multiple decision boundaries. Like, let's say that for a range of 1 to 10, the output of Y is a certain value, and then for a range 10 to 20, it's a certain category of output, and then for 20 to 30, it's another category. So this is really helpful when we have multiple decision boundaries. And so for this, we have set the gamma as auto, but this variable is there is like a intention behind this, that this affects the um, performance of this nonlinear SVM a lot. And so this is also something which can be fine tuned, and you can try different variable values and see which performs best for your data set. Next step, we are again going back to predicting our output. And as we can see, that this is 0.9. So one thing I would like to mention here is that since this is a really small data set, and so there isn't a very visible difference between the performance, and also the performance is slightly random, and like it's not entirely there is not the difference or the effect of different kernels and effect of scaling is not entirely visible on this data set. But as you move to a bigger data set with more number of data, more number of rows of data, you would be able to see an actual difference between actual impact of scaling and applying different kind of kernels on your data set. So this is kind of mostly all I have for logistic regression and SVM. And I would like to hand it back to Sumana for walking you through some of the homework we have for you this week, and just closing remarks. Thank you.
Thank you, Chinmay, for walking us through all the concepts that we learned and seeing how to implement that using Python and existing packages and codes present. So moving on, I want to go over the homework assignments that we have for this week. First up is the concepts. So we learned a lot of mathematical concepts in this session, some which were a little over our heads too, because of the number of how complex the computations are when you start to move your data into higher dimensions. So we would highly recommend you to revisit the theory that we've covered. All slides have reference links too, and we would suggest to definitely use those links to see if they're providing more insight to your topic. And additionally, there are a lot of online resources that can help you out too. But we highly recommend you to revisit the concepts so that you get a better foundation on the math behind logistic regression as well as SVM, both which are regression algorithms which can be used for classification. Second up is revising the logistic regression that we learned. Check out the blog by Towards Data Science. So this website is one of my favorite websites for learning concepts or getting introduced to any new mathematical or machine learning concept. They do a really great job by putting together some very insightful blogs, and I would suggest you to bookmark this website for future reference. But check out this blog by Towards Data Science, where they focus on a data set of social network ads, and use it to predict if someone would buy from the ad or not. And they use logistic regression for this. This will be an easy notebook for you to follow along with. This is the link, and it's been linked over here too. It would be a great way for you to try out the logistic regression skills that you've learned and expand it over a bigger data set and see how it actually impacts your data. There's a lot of homework for this session because of the number of concepts that we covered. We covered a lot of concepts, a lot of complex concepts, so that requires a lot of reinforcement on our end to make sure that we understand what we learned. So next up is revising the SVM that we saw. Chinmay had gone over the IRIS dataset, which is a great starting point for this. I wanted to direct your attention to this blog by Tarek Atwan, where he's using SVM for the IRIS dataset. So try implementing their code yourself. They have the code also uploaded along with visualizations. So this gives like a really nice visualization of non-linearly separable data, and shows how using the RBF kernel in SVM was actually adding value and producing more right answers compared to the linear kernel. So this might be a good place for you to check out this code, and also try it out too, to expand your knowledge on SVM. And last homework, I promise, this one is more on SVM. So there are a lot of data sets which can be really good for SVM. These are data sets that are binary classifiable in a higher dimension vector space. Most popular ones are credit card classification data, which is on Kaggle, and the breast cancer classification data, which is on Towards Data Science. The first link provides you a community which has already uploaded their notebooks. So you have resources available there to plug and play different codes from different notebooks. The second link here is a follow along blog. So the blog entirely tells you start to end how to get the project running. So you can use SVM on cancer classification in this case. And then there are a bunch of Stack Overflow suggestions too for good data sets for SVM. The only hiccup here is there's no solutions present as well as no community help right there. So that is something you can check as you get like better grip on what SVM does and your knowledge gets better. So play around with the hyperparameters in this to understand the effect of the hyperparameters and the kernels when it comes to SVM across different data sets. So that comes to the end of our session. Um, Thank you so much for everyone who joined. If you have any questions post this session, please join us on Slack using the link. Take a look in the chat. You should have received the link there. And use the Help Me channel to post your questions there. Subscribe to the Help Me channel and the Track Events channel so that you're updated about the latest events. And then we have a last and final week of the session coming up. So we highly recommend that you register for it using the link shown on the screen, which should be there in your chat soon. So register for the session, and we look forward to seeing you all next week for our last and final session focusing on model evaluation. We will be focusing on confusion matrices, how to deal with class imbalance, ROC curves, revisit loss functions that we saw, and understand what cross-validation means. This session will be led by myself, Sumana Ravikrishnan, and Tejal Pated. She will be focusing on the implementation portion, and I will be focusing on the concepts portion. So please do register, and I'm excited to see you all next week for wrapping up this series and getting a more wholesome understanding on supervised learning algorithms. Thank you everyone for joining. Have a great weekend, and we will see you next week.